So, let us recall what we were doing in the last lecture. We were proving an important result in the multivariate distribution theory when we have a random sampling from a normal distribution, multivariate normal distribution. So, from the multivariate normal distribution sampling, what we had was x1, x2, xn, a random sample from multivariate normal with the mean vector mu and a covariance matrix sigma. So, using this set of random vectors which are random samples from this multivariate normal distribution, we had formed this data matrix X, which was n by m, and we had the distribution of X to be a matrix normal distribution given by the following parameters, with the mean matrix as 1 mu prime and the covariance matrix of vec of x prime was in Kronecker product sigma. So, under such a setup, we had stated this result and started proving that in the last lecture, that we have x bar, the sample mean random vector, to be given by 1 upon n x prime 1, and the matrix A, which is a constant multiplier of the sample variance covariance matrix in either of the forms with a divisor n or a divisor n minus 1. So, we had this quantity of interest, and the result basically tells us that x bar and A are independently distributed, x bar having a multivariate normal distribution with these parameters with the mean vector as mu and the covariance matrix as sigma by n, and A has got the same distribution as that of z prime z, where the n minus 1 cross m z random matrix is a matrix normal distribution with mean matrix as a null matrix and the covariance matrix of vec of z prime to be in minus 1 Kronecker product sigma, right. That is, in other words, A has got a Wishart distribution m dimensional with parameters degrees of freedom as n minus 1 and the associated variance covariance matrix as sigma. So, we started with the probability density function of this X random matrix, which we had written it in this particular form. Then from this form of the probability density function of the random matrix X, we had made a transformation from X to V. V was given by H times X, and H was an orthogonal matrix with the last row of H given by n to the power minus half in all the positions. So, with this transformation, we were trying to see what's the joint PDF of this transformed random matrix, which is V n by m. So, this H matrix plays a crucial role, the type of H matrix that we had taken in this special form, that of course had implied that the n minus 1 rows, the first n minus 1 rows, this is the first row, second row and n minus 1th row, all these n minus 1 rows of H are orthogonal to this 1 vector. 1 vector is an n dimensional column vector with 1 at all the positions. The Jacobian of transformation was seen to be equal to 1. Now, we had partitioned with a purpose, of course, this V, the new set of random variables forming this random matrix, into this Z and V prime. Z was an n minus 1 cross m random matrix, and this V prime was a row vector m dimensional. So, from this we were trying to see what is the joint PDF of this V of this Z and V transpose. So, in order to do that, we had these calculations done. We had seen that this exponent part, which was appearing here, the exponent part in the PDF, which is this one, this trace of minus half x minus mu transpose sigma inverse x minus mu transpose whole transpose. So, this particular quantity, or in other words, that was written in this form, that it is e to the power trace minus half sigma inverse x minus 1 mu transpose whole transpose into x minus 1 mu transpose. So, we had obtained what is this quantity, which is in the exponent x minus 1 mu transpose transpose x minus 1 mu transpose in terms of the newly defined random variables. So, that we had up to this particular point that this 2, which was here 2 term, which is this term here, is basically equal to 2 is what was sitting in the exponent of that joint PDF. So, from there we had the form of 2 written in this particular form. So, this would imply now that the joint PDF of this Z matrix, which is n minus 1 cross m and V, Now this V is m by 1 vector is given by, now the constant part remains as it is. So this is minus m n by 2, determinant of sigma to the power minus n by 2, and then we had in the exponent e to the power trace minus half of that x minus 1 mu prime whole transpose into x minus 1 mu prime, then that term is basically equal to this term. So we will have that along with that sigma inverse matrix which we have not disturbed. So this is that sigma inverse matrix, this multiplied by z transpose z plus v minus root n times mu into v minus root n times mu transpose. So this is corresponding to this. So we'll have two more brackets to close this particular expression. So this is what we have as the joint PDF of this random matrix Z and the random vector which is V. Now let us write how we can write this particular joint PDF of the transformed random variables in this setup. These constants at the moment are kept as it is, and we will have this, the first term, as trace of minus half sigma inverse z transpose z. So that's the first term, and then we will have with trace here trace of minus half sigma inverse v minus root n times mu, this multiplied by v minus root n times mu transpose, so that this trace comes here, this trace is here, and we will require one more bracket. So we have actually partitioned this particular joint PDF into two parts, one corresponding to this Z random matrix and the other one that is corresponding to the random vector which is V. So let us write this constants accordingly so that we can have well defined distributions corresponding to these partitions. So we will write this as m into n minus 1 by 2. Similarly, we will write this determinant of sigma to the power n minus 1 by 2. Then we will have exponent trace of minus half z sigma inverse z transpose. There is no problem in writing it because what we are doing is trace of a b equal to trace of b a. So we can take this z in the front. So we will have this as the first set of terms, this multiplied by whatever constants are remaining, so that this would thus be, we will have to adjust for this n minus 1 by 2 which we have taken from n by 2. So what we will have here is 2 pi to the power minus m by 2, because this is minus mn by 2 is already remaining. What we have added is m by 2, so we make adjustment for that, and then we will have this as determinant of sigma to the power minus half in order to adjust this particular term here. Let me put a bracket here. So this is the first expression that multiplied by the second expression, and what do we have in the second expression? The second expression for the exponent is e to the power trace of this particular quantity. So we will have that written as e to the power minus half. Now once again realize that we have a trace of these two quantities, so we can write that trace of AB equal to trace of BA. So we can take this term in front and we will write this as V minus root n mu transpose sigma inverse V minus root n times mu. So that we have been able to partition this into two parts. Now what is important to realize from this particular partition are three important things. Now what we have, this is say a function of z here. So this is the density function or the joint density function for this random matrix z, and this is what is the partition corresponding to this v vector. So we have the joint PDF of Z and V written in terms of the product of the probability density functions of this random matrix Z, that is the first expression here, and the probability density function of the random vector which is V, and hence we can say that this random matrix Z and the random vector V are independently distributed. So that is the first thing that comes out from this writing the joint PDF of Z and V in terms of this particular product. The two other things that emerge is that if you look at this particular density, the second one, it is clearly the density of a multivariate normal distribution. So if we consider V, V clearly has got a multivariate normal distribution with what parameters? Now the dimension of V is m. So this V is going to have a multivariate normal m dimensional with a mean vector as this root n mu. So that is what is the mean vector corresponding to this V, and what is the covariance matrix of this V vector? The covariance matrix of V is clearly this matrix which is sigma. So we have written it in that particular form, which readily actually gives us idea about what is the distribution of this associated V. And also note that if we have this as a first part which is corresponding to the probability density function of the random matrix Z, then this reminds us of the probability density function of a matrix normal distribution. So this basically is the density function. So this part, the first part here, so this first part is what is corresponding to the probability density function of a matrix normal distribution, and this second part here is corresponding to the probability density function of a multivariate normal distribution. So we can actually put these things together and write it as conclusion. So this would imply, this means basically this particular expression. So suppose we have this numbered as number 5. So this expression 5 would imply, because that is the joint PDF of this random matrix Z and the random vector V, so that we have obtained it as the product of the two respective probability density functions. So this would imply number 1, that this Z n minus 1 cross m random matrix and V are independently distributed. So that is an important realization which would eventually lead us to proving that x bar and n minus 1 s or a are independently distributed. Furthermore, this V is seen to have a m dimensional normal distribution with a mean vector as root n times mu and a covariance matrix as sigma. And what is the third conclusion that we can draw from that expression? We can also say that this random matrix Z n minus 1 cross m has got a matrix normal distribution with what would be the mean matrix. It is easy to see that this is not centered around any mean matrix, and hence the mean matrix is a null matrix. So this has got a matrix normal distribution with null matrix as its mean matrix. And what would be the covariance matrix? The covariance matrix would correspond from this particular expression, as you can see, that if we had a matrix normal distribution Y with a mean matrix as M and a covariance matrix of vec of Z prime as C Kronecker product D, then here what we will be having is determinant of C raised to the power of the order of D, that multiplied by the determinant of D raised to the power of the C matrix. So here what we have is determinant of sigma only present here. So that C Kronecker product D, we will have C as an identity matrix, and then we will have D as sigma matrix. And then if you look at the order of the I matrix, what we will be having is going to be n minus 1. So we can complete this particular statement that this is a matrix normal distribution with I n minus 1 Kronecker product sigma as its variance covariance matrix of this vec of Z prime quantity. So these are important things to note here. Now we will use these three conclusions that we have obtained from the joint PDF of Z and V in order to prove our desired results. Now, recall that n times x bar is x transpose 1 vector, and what is that equal to? What was the transformation that we had made? We had made a transformation V which was equal to h times x. So, this would imply that our x matrix, the original x matrix, is h transpose V, so that we can write in place of x transpose a V transpose h 1 vector. Now, we have already noted that from the structure of H, what we have, let us recall that also, we had said that H is an orthogonal matrix such that the first n minus 1 rows, whatever they are, have to be orthogonal to the nth row, which has got this special form that all the entries in that nth row are n to the power minus half. So, since this H is orthogonal, first n minus 1 rows of H, the first n minus 1 rows of H are orthogonal to this 1 vector belonging to R to the power n, right. And hence, when we multiply this H matrix with a vector of 1s n dimensional, the first n minus 1 entries, now note that this V we had taken to be of the partition, that we had taken this V as a partition which was Z and V prime. So, that this V transpose would be Z transpose V augmented. So, we will have this as Z transpose augmented with this V vector, and then this H times 1 is going to give us this vector which is 0 on the first n minus 1 entries, and the last entry is going to be this column, this row rather, multiplied by a 1 column. So, we will have n multiplied by n to the power minus half, and that is just equal to this term. And thus, this n times x bar, which is in terms of the original random variables from the random sampling from a multivariate normal distribution, that in terms of the transformed random matrix V and its partitions Z and this V prime is nothing but root n times V, right. So, that this would now imply that this root n times V is equal to n times x bar, that is, this V is root n to the n to the power minus half. So, that would be root n times this x bar vector. Now, we know what is the distribution of V, we have already obtained that, and hence from there we can derive what is the distribution of this x bar. So, this x bar, so this would imply from this observation, using this, that V has got this multivariate normal M root n mu sigma matrix. So, we will have root n times V, which is going to be n times x bar, will have root n times this as n times that, and x bar, which is going to be this divided by n. So, that would be n 1 upon root n times V. We will also have from here, and this x bar from here. So, we are dividing the two sides by n. So, we will have this as n to the power minus half times this V vector. So, this would imply that x bar will follow, because it is just a constant multiplier of this V vector. So, multiplying that by n to the power minus half, the mean vector, the dimension remains the same. So, the mean vector would just be equal to mu, and then we will have 1 upon n times sigma as the variance covariance matrix. So, this proves one part of the result only. Now, let us look at how to use this part and this part in order to prove the remaining portions of this result. Now, note that the A matrix that we had defined was given by 1 x minus 1 x bar transpose whole transpose into x minus 1 x bar transpose. So, we had this as our A. We can write this term by term as x transpose x, this minus x transpose 1 x bar transpose. Then we will have from here a minus just the transpose of this, nothing else. So, x bar transpose, sorry, this is just x bar because we have got this as x bar. So, we will have x bar 1 transpose this x, and then with a plus sign we will have this x bar 1 transpose 1 x bar. So, this is equal to x transpose x minus x transpose 1 x bar transpose, this minus x transpose 1 x bar transpose whole transpose. So, this term is just the transpose of this quantity, this plus n times, this is a transpose here, n times x bar transpose. Now, we can simplify this particular term exactly in the same way as we had simplified a similar expression with x bar being replaced by mu. Let us see what we had obtained there. Now, see, this expression and the expression that we are considering now are similar in nature. Basically, it is differing here. In the present expression, what we have is this mu is replaced by x bar, and there is no other difference. So, we had that term finally reducing to this term. So, that we had that being reduced to this z transpose z plus v minus root n times mu into v minus root n times mu transpose. Now, in the present expression, if we just replace mu by x bar, we are going to have the form of the expression which we are now looking at. So, this term is nothing but we will have that as z, this is z transpose using the transformation here, using the transformation and proceeding exactly as in the previous expression where we had in place of x bar just that mu, and this plus v minus root n, we had previously root n times mu. Now, mu is not present here, what we have is x bar. So, that would be v minus root n times x bar. This, let me see what it was exactly. So, that was z transpose z into this transpose. So, we will have this as a z transpose z, and then we will have this as v root n x bar transpose, right. So, this is what is A, the constant multiplier of the variance covariance matrix. So, this is, just to recall, this is n minus 1 times S n minus 1, or that is n times S n, the sample variance covariance matrix in two different forms. So, what can we say now about this particular expression? Note that what we have obtained is that v equal to root n times x bar. So, since v is equal to root n times x bar, v is equal to root n times x bar, this expression vanishes. So, this is just z prime z. This is so because v by way of construction is root n times this x bar. So, what we have obtained is A, which is n minus 1 times S n minus 1, that is A, is equal to z transpose z, where this z n minus 1 cross m is a matrix normal distribution with a mean matrix as a null matrix, and a variance covariance matrix of vec of z prime is I n minus 1 Kronecker product sigma. So, what does that imply? That simply implies that this A has got the distribution which is same as that of Z prime Z, where Z has got a matrix normal distribution with a null matrix as its mean matrix and In minus 1 Kronecker product sigma as the variance covariance matrix of vec of Z prime. Now, from the second alternate definition of the Wishart distribution that we had given, thus this A follows a Wishart distribution. So, this would imply that A, which is n minus 1 times Sn minus 1, will follow a Wishart distribution m dimensional on n minus 1 degrees of freedom and an associated variance covariance matrix of sigma. This follows by alternate definition of the Wishart distribution. So, what have we proved and what we have not yet proved? Now, we have already proved that x bar has got that multivariate normal distribution. We have also proved that A n minus 1 Sn minus 1 or equal to n times Sn has got a Wishart distribution, Wishart m n minus 1 sigma. Now, note that since this is the last part, so since we have V and Z are independently distributed, these two are independently distributed, this would imply now x bar is coming from V and A is coming from Z, and hence x bar and A are going to be independent. So, this would imply further that this x bar and A, now x bar is in terms of this V vector and A is in terms of this Z matrix. So, that x bar and A are independently distributed. So, that concludes this particular proof of this very important result in multivariate distribution theory. So, that let us once again look back at the result stated. So, we had to prove that x bar and A, this the constant multiplier of the variance covariance sample variance covariance matrix, are independently distributed. So, we have proved this. We have proved that x bar has got multivariate normal distribution mu sigma by n. We have also proved that A has got the same distribution as that of Z prime Z, where Z is the random matrix which is having a matrix normal distribution 0 In minus 1 Kronecker product sigma. That is, in other words, this has got a Wishart distribution on m n minus 1 degrees of freedom. Now, let us put as a note, we are not going to derive this, the density function of a Wishart distribution, how it looks actually, because see, we have not used this particular PDF, but for the sake of completion we will just write this the PDF of a Wishart distribution. So, PDF of this Wishart distribution. Now, suppose we have a random matrix A, suppose that is m by m, suppose this follows a Wishart distribution m n sigma. Now, note that when we say that we have a Wishart distribution m by m, from the definition of the Wishart distribution, either one says that Z will follow a Wishart distribution, Z is or rather A is said to have a Wishart distribution m n sigma, if A can be written as summation I equal to 1 to n y I transpose, where y i's are independent, a multivariate normal distribution with a mean vector as null vector and a covariance matrix as sigma matrix. So, that is the first definition that we had given, or alternately we can say that we will say that A follows a Wishart distribution m n sigma if A is given by Z transpose Z, where Z has got a matrix normal distribution. So, whatever be the definition that we consider, it is easy to see that this matrix A is a symmetric matrix, because either you write A as the Wishart matrix as summation yi prime, which is symmetric, or you write A as Z transpose Z, where Z has got matrix normal distribution, once again that also is symmetric. So, when we talk about PDF of the Wishart distribution, it is basically we are looking at the joint PDF of the distinct elements that are present in this A matrix. Now, how many distinct elements are present in this A matrix? This A matrix is a symmetric matrix. So, the number of distinct elements are m into m plus 1 by 2. So, that when we are talking about the probability density function of Wishart, we are essentially talking about the joint probability density function of the m into m plus 1 by 2 distinct elements of this Wishart matrix. So, let me write this. Then the density function of A, that is of the m into m plus 1 by 2 distinct elements of A is given by the following expression. I will just write it. So, this is 2 to the power mn by 2. This is a multivariate gamma function, multivariate gamma of order m of n by 2, then determinant of sigma to the power n by 2 whole raised to the power minus half. Then we have exponent of trace of minus half sigma inverse A, this into determinant of A whole raised to the power n minus m minus 1, this divided by 2, right. Now, for A to be positive definite, this is what is the probability density function or the joint probability density function of the m into m plus 1 by 2 distinct elements of this Wishart distribution, where this function is a multivariate gamma function, where this gamma this dot is multivariate gamma function. So, although we have not used this particular density in order to derive any results as such, for the sake of completion, this is what is the density function of a Wishart distribution. Now, the next thing that we are going to look at is the characteristic function of Wishart distribution. So, let us look at how this characteristic function actually looks like. Let me state the result first. Suppose we have A following a Wishart m n sigma, then the characteristic function of A, now once again this is the joint characteristic function of the distinct elements, that is the joint characteristic function of the m into m plus 1 by 2 distinct elements of this random matrix A. Let me write them as some notations of A, say A I j. Now, for the distinct elements, what we will be looking at is one direction only. So, these are basically the random elements what we have. So, the characteristic function of this is given by the following. Let us denote that by phi A of at the points this script theta matrix, which is given by expectation of e to the power I times summation double summation j less than or equal to k equal to 1 to up to m. Then we have this as theta j k times a j k. That's basically is the joint characteristic function, because we are looking at all the distinct elements. So, that this would just be given by this j less than or equal to k of these random quantities. In this double summation, we are only looking at the distinct elements in one direction. So, we have that to be equal to determinant of an identity matrix of order m, I m minus I times gamma times this sigma matrix and whole raised to the power minus n by 2. So, this is what is going to be the characteristic function of a Wishart distribution, where we have these notations that we have already introduced, where script theta is a matrix which is having elements as theta I j. It is a symmetric matrix with theta I j equal to theta j I is a real symmetric matrix. So, this we have a real symmetric matrix, and this matrix gamma that we have defined here is having elements, say gamma I j for both these quantities I j equal to 1 to up to m. Now, this gamma I j's are such that this gamma I j is equal to 1 plus delta I j into theta I j, and this delta I j is the Kronecker delta, that is this delta I j is equal to 1 if I is equal to j and is equal to 0 if it is otherwise. So, this what is the statement of the characteristic function of a Wishart distribution. If we have a Wishart distribution Wishart m n sigma, then the characteristic function of A, which is also actually the characteristic function of the joint or the joint characteristic function of the m into m plus 1 by 2 distinct elements of this matrix A, which are A I j, which is given by phi A script theta, is going to be of this particular form. We now look at proving this particular result, that is deriving that the characteristic function of the Wishart really is given by this. So, let us look at proving this important result, which gives us the characteristic function of a Wishart distribution. So, we have this A to follow a Wishart distribution, Wishart m n sigma, and for that what we have is this phi A script theta, which is the characteristic function, is expectation of e to the power I times double summation j less than or equal to k equal to 1 to up to m, which is theta j k times a j k. So, let us write this in the following form, that it is e to the power, we remove this particular restriction, we write it as half of this. So, we will have j equal to 1 to m, k equal to 1 to m, and then we will have that in order to adjust, we will have a delta j k times theta j k times a j k, right. So, if we remove this restriction that j is less than or equal to k, in order to adjust that, what we have introduced is this Kronecker delta j k, and we have written it in this particular form. Now, this form will lead us to, now note that this particular term here 1 plus delta j k into theta j k is nothing but gamma j k. So, we will have e to the power I by 2 summation j equal to 1 to m summation k equal to 1 to m, and then this is gamma j k, the notation that we had introduced, that gamma j k is 1 plus delta j k times theta j k. So, we will have that to be given by this. Now, what is this expression, by the way? If we look at this double summation here, j equal to 1 to m, k equal to 1 to m, theta gamma j k times a j k. So, gamma is that matrix which is holding this gamma I j terms, and A is the matrix which is holding this A I j terms. So, if we look at this double summation here, it is nothing but trace of the product matrix gamma with A. So, we can write this as e to the power I by 2, then we have trace of A times gamma matrix. You can write it as A times gamma, or you can write it as gamma A, because we have a trace here, so it does not matter. Now, let me write this as equation number 1 in this proof. Now, since we have A to follow a Wishart M n sigma, we can write A as Z transpose Z either, where this Z has got a matrix normal distribution. This has got Wishart M n sigma. So, we will have this as a null matrix and I n Kronecker product sigma as its variance covariance matrix, or we can write this. So, these are the two alternate definitions, alternate equivalent definitions of the Wishart distribution that we had given. One can write this as summation Zi prime I equal to 1 to n, where Z1, Z2, Zn are IID, independently and identically distributed multivariate normal random vectors with mean vector as null vector and a covariance matrix as sigma. So, these two are known facts. Now, this thus will lead one to the following. We can write this as expectation of e to the power I by 2 trace of, in place of A, we can write this as Z transpose Z times this gamma matrix, or we can write that equivalently in terms of this Z I vectors as expectation of e to the power I by 2 trace of summation I equal, let me have this as j, because we have I is the imaginary part, which is imaginary number, which is square root of -1. So, we have j equal to 1 to up to n Zj Zj prime of this particular term. It would be advantageous actually to use this particular form in order to prove this result. So, let me use this particular form, that is, we have phi a script theta, that is given by expectation of e to the power, the expression there was I by 2. One can write this as summation Zj prime gamma Zj, j equal to 1 to up to m. How have we obtained this particular expression? From the previous expression, if we look at this, so we can take the trace, there is a gamma matrix somewhere which is slipped out, this is that gamma matrix. So, we will have here, once we have, this is trace of this Z A quantity and that multiplied by this gamma, and then we have the brackets closing. This is first bracket closing here, and this is the exponent bracket closing here. So, we will have trace of this particular term here. Now, the gamma can be multiplied out here term by term. So, we will have trace of summation Zj, Zj transpose times gamma, and then trace of AB equal to trace of BA. So, what we will be having here is trace of this Zj, Zj transpose gamma will be equal to trace of Zj transpose gamma Zj, and that is what is written out here. So, we will have that expression as I by 2 remains outside, summation I equal to 1 to n Zj transpose gamma Zj. Right. Now, here this Zj's are IID, multivariate normal random variables, each with a multivariate normal distribution with a mean vector 0 and a covariance matrix as a sigma matrix. So, since these Zj's are independent, one can write this in terms of this product, well, without that, this j equal to 1 to n. So, we are looking at these expectations term by term. So, expectation of e to the power I by 2, there is a trace sitting here, I by 2 trace of one of these quantities, that is this Zj transpose gamma times this Zj. Right. Now, note that this Zj's are all IID random vectors, and hence whatever the expectation for one Zj, that would be the same for the other zj terms, and hence we can write it, say expectation of e to the power I by 2 trace of zj transpose gamma zj. So, say let me just write this as one of these zi's, say I write this as z1. So, whatever is the expectation of this term here, expectation of this exponent for z1 is going to be the same for any of the j's which is in this product here. Why is that so? Because zi's are IID random variables, and hence this expression would just be raised to the power n, nothing else, right. Now, we have to evaluate this particular expression. Now, let us make a transformation. Let us make a transformation. Say y, which is equal to sigma to the power minus half times this z1 vector. Now, remember z1 has got a multivariate normal, mean vector 0, covariance matrix sigma. So, this y will follow once again a multivariate normal distribution with the same dimensionality as that of the z1 vector. So, it would be this with a mean vector as a null matrix, null vector, and the covariance matrix as sigma to the power minus half covariance matrix of z1, which is sigma times sigma to the power minus half transpose. So, it is a symmetric matrix. So, this is equal to this. That is, what we have is this a multivariate normal distribution M, and this is just an identity matrix, right. So, we can replace this zi's by the corresponding yi terms. Now, if y is given by sigma to the power minus half z1, this would imply that z1 random vector is this being pre-multiplied by sigma to the power plus half. So, we will have this sigma to the power plus half into this y vector. So, let me have this as number 1. So, this will imply that this number 2, I am sorry, this is number 2. So, this number 2 is expectation of, this is raised to the power n. So, expectation of e to the power I by 2, then a trace of z transpose z1 transpose. So, I can just remove this trace as well, because this is a scalar quantity out here. So, that we can, since this is z1 transpose gamma z1, this is a scalar quantity. So, we can either write that as trace or drop that trace, because this is now going to be a scalar quantity. So, what we have this as I by 2 z1 transpose gamma times this z1, this raised to the power n. Now, this in terms of the y random vector would be expectation of e to the power I by 2. So, z1 transpose would be y transpose sigma half gamma sigma half times this y vector. So, this bracket closes here and this bracket closes here. This is for this is for this, and we will have this raised to the power n. So, the characteristic function thus is of this particular form. Now, let us try to see what is that special about this particular matrix sigma half gamma sigma half. Let me give this equation number 3 and move on to realizing what is this. We notice that this sigma half gamma sigma half is a real symmetric matrix. So, there exists an orthogonal matrix H, say, such that we will be having this H sigma half gamma sigma half H transpose to be given by a diagonal matrix lambda 1, lambda 2, lambda m, let us denote that by a capital lambda, where this is basically the spectral decomposition of this real symmetric matrix, where lambda 1, lambda 2, lambda m are the eigenvalues of this sigma half gamma sigma half matrix. And what is H? H is that orthogonal matrix which is having the orthonormalized eigenvectors corresponding to these eigenvalues of sigma half gamma sigma half matrix. So, we will have this, the spectral decomposition corresponding to that matrix. Now, using this matrix, orthogonal matrix H, make a transformation, consider a transformation from Y to say a random vector V, which is given by H times Y. Now, H is this orthogonal matrix. We know what is the distribution of Y. What is the distribution of Y? The distribution of Y is multivariate normal with a mean vector as null vector and a covariance matrix as Im. So, this will lead us to what is the distribution of this V. This V is going to be, now what is the order of this H matrix? H matrix naturally is m by m. So, this is an m by m. So, we will have this multivariate normal m with a mean vector as a null vector and the covariance matrix as H, covariance matrix of Y, which is an identity matrix, times H prime. Now, H is an orthogonal matrix. So, we will have that once again to be given by this Im, an identity matrix of order m. So, this would imply this phi a script theta is equal to what we will take forward is this particular form, and then in place of Y what we will be writing is V. So, we are making that transformation. So, that it would be, a bracket is outside, expectation of e to the power I by 2, then we have this. Now, from here this V is H times Y. So, our Y is going to be H transpose V, right. So, from here what we need to look at is what is Y transpose. So, that it would be V transpose H, then sigma half gamma sigma half, this remains as it is, that multiplied by Y vector, and Y vector is nothing but H transpose this V vector, right. So, this is what is there in the exponent. This term closes here and this term closes here, this is raised to the power n. So, what we have here is that, note that this particular term here, which is H sigma half gamma sigma half H transpose, is nothing but this gamma matrix. So, we will have this as expectation of e to the power I by 2 V transpose, then this capital lambda matrix, where because that is what is given here, that multiplied by this V vector, and then that is raised to the power n. So, what would that be equal to? This would be equal to I by 2. Now, V is that particular m dimensional vector. Now, this capital lambda is this diagonal matrix which is holding the eigenvalues lambda 1, lambda 2, lambda m. So, that this is just going to be equal to summation this lambda j V j square terms. What are these V j's? This j is equal to 1 to up to m, that is the order of this V vector. This V vector is m by 1, and hence the elements are V1, V2, Vm, and these basically are the square of those entries out here. So, that we will have this to be equal to this. Now, note that what is that special about this Vi entries? Now, this V vector, which is our V1, V2, Vm, this follows a multivariate normal m dimension with a mean vector as null vector and a covariance matrix as Im. So, this would imply that this V1, V2, Vm are IID normal 0 1. So, that is that these V1, V2, Vm's are standard normal random variables. So, this would imply that V1 square, V2 square, Vm square, they are the squares of the standard normal variates. Since V1, V2, Vm are IID, and so will be V1 square, V2 square, Vm square. These are IID what random variables? These are chi-square on 1 degrees of freedom random variables. So, what we have obtained, what we have reduced this cumbersome derivation of this deriving the characteristic function of the Wishart distribution, this we have derived in terms of the characteristic function of just a simple chi-square random variate on 1 degrees of freedom. So, that we can say that this, since this Vj square has got a chi-square on 1 degrees of freedom, the characteristic function of this Vj square is given by phi Vj square t, that is equal to 1 minus 2 I t, that raised to the power minus half, right. So, we will use this characteristic function. Now, each of these V1 square, V2 square, Vm square, they are having the same characteristic function because they are IID random variates, and hence the IID chi-square, central chi-square on 1 degrees of freedom random variates, and hence the characteristic function is going to be the same. So, we will use this characteristic function of the central chi-square distribution and just plug in the values of those here in order to get to the final form of the Wishart distribution that we will see in the next lecture. Thank you.